Welcome back to Applied Mathematics. In this video, we're going to be solving linear equations. I don't have much to say in an introduction. Let me get my head out of the way and let's dive into it. A linear equation and I should stress here we're talking about a linear equation in one variable. There can be linear equations in 2, 3, and more variables, which we will talk about a little bit later on in this course. But a linear equation in one variable is any equation which can be written in the form ax plus b equals c for known parameters a, b, and c. All right. So if you're not accustomed to working with this, the hardest thing to understand in the conversation here, a, b, and c, we are anticipating are known values. Those are things that have to be given and put into the equation before we get started. X here then is our only variable. And so if we can identify a value of x, then we have a solution to our equation. We have looked at solving equations in this form previously, right? Something like 3x minus 14 equals 23. I can first add 14 to both sides of the equation. And then get x by itself by dividing both sides of the equation by 3. So one interesting thing about this particular equation, because all of the parameters in the equation that was given to us are small whole numbers, I am going to assume that we're talking about exact values here. Things that only a mathematician can appreciate. We're not talking about measurements or approximations in this particular problem. And so when I get my result, 37 over 3, I'm leaving it as a fraction. There's of course no reason that the parameters in a linear equation cannot be approximate values. And certainly in most of the applications we're going to be looking at, we're going to be dealing with measurements. So how about 4.72x plus 19.5 is equal to 32.78. Right. I'm also going to use this as an opportunity to start being a little bit less verbose, writing out my step-by-step approach. I know I'm going to subtract 19.5 from both sides of the equation. I know that on the left-hand side of the equation, those are going to cancel out. So I'm going to be lazy and not write it on the left-hand side. I will only write it on the right-hand side. Then, since these are approximate values, when I do this calculation, 32.78 minus 19.5, my calculator tells me it's 13.28, but I'm going to round. Rule on subtraction is round based on your worst precision, which is to the nearest tenth here. And I'll write that result as 13.3. Let's make that look like a 3 and not like a frightening glyph. 13.3. Then to get x by itself, I divide both sides of the equation by 4.72. I let my calculator do the work for me. 13.3 divided by 4.72 comes out as 2.8177966, etc. The two parameters that I am dividing both have 3 significant digits, so I keep that same accuracy. I round my result here to 3 significant digits. 2.82 is the solution that I end up with. All right, so exact values, approximate values, doesn't matter, the process looks the same. And we know how to solve an equation like this. We've seen them before. So how am I going to do an entire video on solving linear equations when we already know what we're going to be doing? To answer that, I'm coming back up to the definition here, and I want to highlight one other thing in this definition. A linear equation in one variable is any equation which can be written in this form. It does not have to be written in this form. And so a lot of the struggle of solving linear equations is getting them into this form in the first place. As we look at equations that are linear equations but don't look like them, a lot of our effort is going to go into using the properties of algebra that we know to rewrite the equation to make it look like a linear equation. The general strategy for doing this is to first collect all of the variables on one side of the equation and simplify. You should at that point have exactly one variable appearing in the equation. If there's more than one variable appearing in the equation, you haven't finished this step yet, or possibly you don't have a linear equation. Once you have that, you can then collect all of the constants on the other side of the equation and again simplify. So you have some number times x equals some number at the end of that step. Dividing by the thing multiplied by x will get you x by itself. I also want to point out here, I did not necessarily say collect all the variables on the left and all the constants on the right, although that will be what we do most of the time. We have the symmetric property of equality that tells us that if we swap the order and switch the variables on the right and the constants on the left, the process works the same and there's nothing different. So with that in mind, let's look at something that's a little bit messier. Four times the quantity 3x minus 7 equals 9x plus 12. I notice here that there are variables on the left-hand side and on the right-hand side. And so the first thing I want to do is get us from having two variables to having only one variable appearing in the equation. And it's easier than it might seem at first glance. I can use the distributive property to get rid of those parentheses on the left-hand side. 4 times 3x is 12x. 4 times minus 7 is minus 28. Then I can move all of my variables to either the left or the right. Sometimes the equation is going to push you very strongly in one direction or the other. In this case, there's not really much difference. If I move everything to the left, I will have a positive coefficient, and that makes life ever so slightly easier. So I've got a 9x over here. To get rid of 9x, I'm going to want to subtract 9x. So I have 12x minus 9x minus 28, and then just 12 left on the right-hand side. 12x minus 9x, those are some like terms I can combine, and that gives me 3x minus 28 equals 12. At this point, I have arrived at something that looks like a linear equation. That's a very good sign. That tells me that I'm going in the right direction. From here, we can use the usual procedure. Add 28 to both sides of the equation. 3x equals 12 plus 28, and 12 plus 28 is 40. And get x by itself by dividing, and we get that x is 40 over 3. Once again, since all of the parameters in the original equation were small whole numbers, I am assuming that everything is an exact value, and so I'm going to leave my result as a fraction. Pay attention to instructions. When I write problems for you to try, I do my best to explain very clearly when you have exact values, when you have approximate values. I say those phrases explicitly. But when you're looking at homework that I'm not the one that wrote, sometimes it's a little bit hard to tell. Sometimes not all of the sources that we use actually state those things as clearly as they should. Here's another example. 3 times the quantity 6x minus 5 equals 9 times the quantity 2x minus 8. I have parentheses on both sides of the equation, which is going to make things a little bit interesting, but we can, once again, use the distributive property. 3 times 6x is 18x. 3 times minus 5 is minus 15. 9 times 2x is 18x. 9 times minus 8 is minus 72. Right? I now have x on both sides of the equation. That's an issue. That's something that I want to address here. And so I'll subtract 18x on the left and on the right. And then something a little bit weird happens. I've got 18x minus 18x on the left-hand side. That's 0, leaving behind minus 15. I've also got 18x minus 18x on the right-hand side. That's also 0. It leaves behind negative 72. I hope that it immediately jumps out to you that negative 15 and negative 72 are not the same number. This equation is false. We said absolutely nothing about the value of x. And in saying absolutely nothing about the value of x, we arrived at a false statement. This is an equation that is never true. This is a contradiction. A contradiction is never true, no matter what values of variables you use, which means that there is no solution. You may come across, as you are looking at various sources, various problems, especially if you're searching online for additional help, the solution set here is called the empty set. And the symbol for the empty set is a circle with a slash through it. All right, this is a contradiction. There is no solution. The solution set is the empty set. Those three phrases are equivalent. You can use any one of them. I tend to go with there is no solution. But I wanted to mention all of them because if you're looking at various sources, if you're looking at help elsewhere on the internet, you may come across any of them. They all mean the same thing. Right? When we were talking about types of equations, we talked about contradictions. At the exact same time, we were also talking about another type of equation. So if I take a look at 4 times the quantity 3x minus 9 equals 3 times the quantity 4x minus 12, and I again use the distributive property to clear up things on the left and right side of the equation. 4 times 3x is 12x. 4 times minus 9 is minus 36. 3 times 4x is 12x. 3 times minus 12 is minus 36. And here we have the exact same thing on the left-hand side and the right-hand side of the equation. The reflexive property of equality tells us that this equation must be true. Right. This equation is an identity. All real numbers are solutions to this equation. Or this equation has infinitely many solutions. Again, all three of these statements are valid, and looking at different sources, you will see any of them used. I tend to use the statement that all real numbers are solutions. And the symbol for all real numbers, that blackboard bold or double stroke R, is a nice shorthand for that as well. Again, there's no one right answer. All of these are equivalent. I tend to write out the phrase all real numbers, or even all real numbers are solutions. But they're all equally valid, so I wanted to make sure you saw all of them. I want to go through one last example here. (3x minus 5 equals 7x). This one is a lot easier than the ones we just looked at. Nothing weird happens on this one at all. But problems like this, I very often see students panic about. So I wanted to walk through it. You've got a couple of options here. I'm going to stick with, let's move the variable to the left-hand side, which means I need to subtract 7x from both sides of the equation. 3x minus 7x is negative 4x. 7x minus 7x is 0. There's nothing else over there, it's just 0. So, a couple of things here. Yes, you can have a negative coefficient on your variable. It is perfectly valid, there is nothing wrong with it. Yes, one side of your equation can be 0. And in fact, there's a lot of times when that's incredibly useful. Each of those I've seen very often cause students to panic, so I wanted to go through this example to encourage you to not panic. This is perfectly normal. Everything is fine. Right, but the next step is to add 5 to both sides of the equation to get the term with x by itself, and then divide by the coefficient, which in this case is negative 4. So 5 divided by negative 4, which we will more typically write as negative 5/4. All right, that's all I've got for this one. As always, thank you for joining me. Hopefully, again, mostly familiar concepts for you. It may be a while since you've thought about contradictions and identities. They don't come up all that often, but they can come up. And when they come up, it almost always means something interesting is happening. So being able to identify that, being able to not panic and understand that that's just a thing that can happen, certainly can be important. As always, thank you for watching, thank you for joining me on this video, and I'll see you next time.